Welcome back to this channel. In my last video, I showed you how that the magnet, you could make an electromagnet, which we otherwise call a temporary magnet, by passing current through a coil of wire that we call a solenoid, which typically looks like this. If you have this, you make a coil of wire, we pass current, for example, in this direction. Current is going to move in this direction. Now, if current moves in this direction, it means that this is going to be our north and this is going to be our south. And I've showed you how to do that. If you look in this from here, it's going to look like it's going in the anti-clockwise direction. Where the current seems to be going in the anti-clockwise direction is going to be your north. If you look here, the current is going to be approaching like this. That is the clockwise direction. It's coming like this, anti-clockwise. So if it's coming like this, then it's going like this in this direction, in this side. That is clockwise. So where the current appears to be going clockwise, that is the direction of what? South. Does that make sense to you? All right. So we have established that if we create a system like this, that this solenoid is going to create what? Is going to become an electromagnet, which is basically what? A temporary magnet. Temporary because once we open the switch back, the system does not run again. It's no longer a magnet. Now, I mentioned something very profound, which is that how do we increase the magnetic field or the magnetic property of this guy, of this our solenoid? There were three things I talked about, or two things basically I mentioned. If you increase the number of turns or coil of the wire, you increase the number of turns or coil of the wire or the solenoid, you are going to increase the magnetic field. If number two, you also increase the strength, the current, the rate of flow of charge, you increase current. That is, increase the magnitude of the current. What is going to happen? Increase current I, you are going to increase the magnetic field strength of the magnet. Is that okay? I'm going to increase magnetic field strength. Then the third thing is that, I didn't mention this, which I forgot, now is that if you place an iron core, a soft iron core, now you might be thinking that why the choice of word soft. Now soft because soft iron core, if you remember in our introduction to magnetism, I'm going to link that video in the description. Please follow the series. It's very simple and full, everything you need is just available. Is that okay? For your JAMB and other exams. Is that okay? Now, the soft iron core is because the choice of soft is because soft ions are easy to magnetize. So they are easily magnetized. Of course, they do lose their magnetism quickly. But that is the reason why we are choosing a soft iron core. Is that okay? To magnetize. If we are choosing steel is hard to magnetize, but hard to demagnetize as well. So that's why we're using a soft iron core. Core because it's going to be placed in the center of this solenoid. So you insert a soft iron core here. Now, why is the strength of this magnetic field going to increase? Because now there's an iron core here that has magnetic domain. So the magnetic domain we align, form a magnet, and of course, the wires again around it, with the current passing through them, will also form a magnet. So two magnetic fields combined will increase the strength of this solenoid. Does that make sense? Or this electromagnet. Does that make sense? All right, now let's get into the motor effect of electricity. You're going to see why I introduced this again, which is the introduction of soft iron core into the solenoid. Okay. Now, what is the motor effect of electricity? The motor effect of electricity basically relates to how the interaction between electric field and magnetic field can lead to, when they interact, their effect is called the motor effect. What happens when electric field and magnetic field interact? Okay, now join me on the board and see. Let me show you a typical example of what I mean. Now, if I have something like this, if I have two magnets, for example, Okay, let's manage this. So I have something like this. Okay, just watch me, just watch me. Now this side of the magnet, let's say it was the north, and this side of this magnet was the south. Two magnets facing each other. It means that as they are close to each other like this, electric field is running, magnetic field is running in this direction from north to south. We know this, right? Good. Now, so that those lines I drew now, they are the lines of magnetic field. If I now put a wire, if I put a wire that is connected to an electric source, it means that the current is flowing, this positive, negative, it means that current is flowing in this direction, right? Current is going like this. Now, there is going to, you already know from the first right-hand rule that we said that a current carrying conductor has what? Magnetic field around it, right? Discovered in 1820 by Hans Christian Ørsted, that a conductor that is carrying current has magnetic field around it. You already know that, right? So if you don't know that, I'm going to link that video also in the description. Do well to view it. Now, since a wire like this that is carrying current, it has magnetic field around it. It means that here too, magnetic field is flowing around this wire. Does that make sense? If magnetic field is flowing around this wire, and look at this system where two magnets are brought together, this will be the north of this will be the south of this. So these two magnets are brought together, and also fluid. All right. So two magnets are brought together. It means that magnetic field is going from north towards south. So, and magnetic field is also running around this guy. Does that make sense? So if magnetic field is running around this guy, it therefore means that two magnetic fields are going to interact here. And the moment they interact, they are going to create a force that will be felt by this wire or this conductor. Provided that these two are permanent magnets and they have magnetic field flowing from north to south, which is basically what we always have. Now, if I put a wire around into this magnetic field and I connected to a voltage source and current was flowing in that wire, what will happen is that this guy is going to experience a force and is going to move in a direction. Okay, quickly, let me show you the direction it's going to move. The rule we are going to use to learn it is called the Fleming's left-hand rule. The Fleming's left hand rule. All right, so and it's basically like this. You use your left hand, you put your, okay, let me try to draw it so that you will have what I'm understand what I'm trying to say here. The Fleming's left hand rule, you're gonna have, oh no, the thumb, right? It's going to draw the thumb. All right, don't manage this one. Eh? 1, 2, 3, 4, 5. Okay. Okay, let's just manage this. Okay, your thumb is going to have nails here. That will have nail here. All right. So look at this. Now, this is the Fleming's left-hand rule. Now, it says that if your left hand is positioned such that your thumb is pointing in direction of the motion or force, the direction the force we push the wire or the conductor, your right hand is going to, now remember, your right hand is always going to be pointing in direction of B field. Is that okay? Magnetic field. Your forefinger rather, magnetic field. While this guy, your middle finger is going to point in direction of the current. Okay, so I said something to my student. I said, when someone does like this to you, just say, it's giving you current. It's not saying anything vulgar. Is that okay? So it's giving you current. All right, anyways. So this guy, is the system of the Fleming's left-hand rule. Now, this guy is going to help us to know the direction in which this force will move. Now, in a minute, I'm going to show you a demonstration done by Professor Walter Lewin on this thing. Is that okay? So, and I'm going to be explaining what is going on there. Now, a current that is moving, so this hand, so this thing is basically what I've drawn here. This hand will represent the direction of current. This one here will represent, so let me show it well. So this is my hand, this is my left hand, as you can see. This hand is going to represent current. So it's coming, that thing I drew now is looking like this. This hand is representing current, this hand is representing magnetic field, and this hand is representing the force. Are you clear on that? So if we want to know the direction of that wire you can see there. We want to tell the direction in which the wire will move. Now this is how we do it. We are going to align our hands, our fingers, in the directions of those quantities that you see there. Now current is going like this. Where's your current hand? This hand, right? No middle finger for your enemies, that kind of thing. This guy is going to be the current hand. So current is going like that. So let's align our hand in the direction of current, okay? Now magnetic field, this is our hand of magnetic field, is going that way. So magnetic field is going that way. So magnetic field is going like this. And B field is going, magnetic field is going like this. Current is going like this. Okay, how do we put it? Okay, like this. So you see, I'm turning my hand upside down so this is my B field. I don't know if you can see this. This is my B field. This is my current, rather. Current is going this way. And magnetic field is going from here to here, from north to south. Okay, so we have this. Then if your right hand, if all your fingers must be at 90 degrees, where will be your force? Your force will be downwards, if you look at it very well. So let me come to the screen again. So you see this, you must align your hand such that all of these must be at right angles to each other. Look at it. They must be at right angles to each other. So this one is going to be at right angle to this guy. This one will be at right angle to this guy. This guy will be at right angle out of the board and on this end. So they are all at right angles to each other. So if I said the magnetic field is going like this, magnetic field is going from, let's just say from right to left, is that okay? If magnetic field is going from right to left, and this magnetic field, magnetic field, and current is going in that direction. So current is going in that direction. It means current is going something like this. Your hand must be like this. So if current is going in that direction, magnetic field is going like this, then your force will be felt where? Downwards. So force on this thing is going to be downwards. Does that make sense? So what if you reverse this? So if I reverse this and made my north here, made my south here, made my south here, I made my north here, and current through this wire is still going into the board, for example. Where will the force be felt? Magnetic field is not like this. So you first align your magnetic field. The magnetic field is going like this. Current is going in that direction. You see, it has already aligned by itself. Where will the force be felt? Upward. So this wire will move up. Here, this wire will move down. Now look at this demonstration.
The wire in orange within the huge black magnet. Current runs through the wire when he turns on the switch. The wire is pushed up or down when current runs through it.
3, 2, 1, 0. Very clear. You saw it come out. Okay.
Alright, welcome back. Now I believe that you have seen that demonstration and you saw how that wire jerked up and jerked down in the magnetic field due to the interaction between the electricity that is flowing here and the magnetic field that is produced by the permanent magnet. Now, let's go to the mathematics of things now. Now that force, this force that is felt downwards here, the force on that wire is actually equal to the current, that is the product of the current in the wire, the length of the wire, and the magnetic field of the wire, sine theta. Now there is an angle because of this reason. Now if my magnetic field was going from north to south, everywhere here, from north to south here, and my wire was placed like this in magnetic field, there is an angle theta everywhere here between the magnetic field lines and my current the current that is flowing. Is that okay? Or this, the position of the length of the guy, the length of the wire. Is that okay? You know, the current is going to flow the length of the wire, right? So there is an angle between them here. So because of that, the closer to perpendicular the length is, the angle is, or the closer to perpendicular the length, this angle between the direction of current through the length of the wire and the magnetic field, then the higher the force that will be felt by this guy. What that means is this: if theta is perfectly perpendicular, that is, the angle between them is perfect 90 degrees, then in that case, what you're going to have is this, that F, your force is going to be what? ILB sine, or BIL, maybe that's the common convention you see, BIL sine 90. And recall that sine 90 is equal to 1, so F is going to be equal to BIL. Is that okay? So there are 3 things, or up to 4 things, that will determine the strength of this force that will be on this wire. So let me clean this part. Now, what are the factors that will determine the strength of this? In my next video, I'm going to really show you, I'm going to break down in my ACOP series, yes. And watch out for the ACOP series. ACOP standing for, or ACOP rather, ACOP standing for Anybody Can Understand Physics. We're going to be starting that series soon, and watch out for the series. Is that okay? I'm going to be explaining why the force is on this guy, on that conductor. I'm going to show you how the force is actually acting on it. Alright, but in this series, let's just continue. We said that there are some factors that determine the strength of this force. Now, the magnitude of the force is depending on 3 things. As you can see here, it's depending on the strength of magnetic field, or magnetic field strength. So it's depending on magnetic field strength. It's depending on the magnitude of current. So the higher the current passing through the wire, the higher the force that will be felt. It's also dependent on the length of the wire. So the longer the wire, the longer the conductor or wire, the higher the force that will be felt. And also, the closer to perpendicular, that is, the closer to 90 degrees, the B field and length of conductor is, then the higher the force that will be felt. Is that okay? The higher the force that will be felt. Okay, so now this is what we have for motor effect of electricity. So how do we now generate motor effect? First, you have understood now that when you place a wire in a magnetic field and the wire is carrying current, then a force will act upon that wire. Okay. Now, using this same system, I don't want to clean it. Let me show you the motor, which is called the DC motor. Yeah, let me just show you. I was not supposed to clean that. So this is our north. So you now know the direction of magnetic field, right? You now know the direction of magnetic field. And you can test yourself with so many questions. Is that okay? On that, the direction of wire and all of that. Is that okay? So for example, if I have a magnetic field that was flowing from north to south here, like this. And my wire, my current is flowing into the board. My wire is entering into the board like this, so that current is going in that direction. So what do? Align your hand, your left hand rule. Remember, it's the left hand rule. Align your hand such that B field is like this. Current is into the board like this. So it was supposed to be like this because this one is out of the board. Current is out of the board here. So you turn it into the board. Once you turn it into the board, where is the force? The wire going to go down. Is that okay? So test yourself in various ways. You're going to understand it. Now, so just the same way that when we are talking about how that a current carrying conductor, that there was a magnetic field around it, what did we do to it? We now coiled it, right? Let's make a coil out of these two. Let's make a loop rather, not a coil yet. Let's make a loop. Coil is several loops. Is that okay? Coil is several loops. So I want to make a loop of my wire now. I want to make a loop. So let's make a loop that will look like this. This is the typical diagram you see in your textbook. So let's make a loop that will look like this. Now the loop is going to be placed in a magnetic field like this. That looks like this. I place my loop in a magnetic field that will look like this. Okay, so I placed my loop in this magnetic field. Magnetic field, don't forget, is going in this direction. So I don't want to draw it so that it will not, make the diagram look somehow. Then I now connect my wire in this direction. I connect my wires. So using the same analogy, where is this guy going to flow? Current is going to flow. Current is going to flow from positive, conventional current will flow from positive to negative, right? So current is going to come like this. So watch. So on this side, please follow me now. On this side of the magnet, on this side of the loop, current is going to flow in a particular direction, which is upward, right? On this side of the loop, current will flow downward. Is that okay? We want to see how it will affect this guy. That's why we're choosing only those two sides of the loop. So on this side of the loop, let's see what happens. Current is going like this, right? If current is going like that, so it means that current is going like that, magnetic field is going like this, right? So my hand is pointing this way. Where will this side of the magnet of the loop, where will it go? To go down. Is that okay? For this side of the loop, current is coming like this towards me. Magnetic field is still going like this. Where will this side go? Up. Does that make sense? Okay. So let me show you again. I said that. So look at this side of the loop and look at this second side of the loop. So on this side, this first side of the loop, current is going in that direction, right? And magnetic field is going from north to south. Current is going in that direction. This is my current and magnetic field, and current is going in that direction, and magnetic field is still going north to south. Then where will the force go? The force will go down, right? The motion of the that place will be down. Now on this other side, the current is coming out. Magnetic field is still going that direction. Where will the force be felt? To be felt up. So that loop of wire will move up. So what do you see? You're going to notice a rotation there. Since this side is moving down, this side is moving up. So what will happen? Then it causes a rotation. So that is how a rotor works. Is that okay? That is how it works. But in a rotor, there are several coils of wire, and I'm going to bring that in. But first, let's talk about the advancements that were brought to this thing. You will notice that if this thing now begins to rotate, it means that rotation is going to happen to this guy, right? If this thing begins to rotate, if this coil of wire begins to rotate, what will happen? If this coil of wire begins to rotate, you are going to notice that this thing will tangle up. Is that okay? It's going to tangle up. So what they do is this. Then they recreate the system such that we still have our loop. Is that okay? But the loop will no longer be directly connected to the wire again. It's going to first be connected to what is known as a commutator. All right, so this guy is going to be connected inside here. This guy is going to be connected on the other side inside. Is that okay? So then we now have what we call carbon brushes attached to it like this. We have carbon brushes I'm going to tell you what that is. Then we have carbon brush here too. Let's manage this side here. I made it look like this, so let's not change it. Okay, so we now have carbon brushes attached here. So what is making contact between the battery and this coil of this conductor here? It is the carbon brushes. The carbon brushes are put there in order to make contact. That is the use of the carbon brush. But this other guy here, this guy here is called, that looks like a ring, right? It looks like a ring. It's called a split ring. Because if you notice, you are going to notice that there is a space between them here. There's a space here. There's a space between them here. There's another space here. So we call it the split ring. Split rings, both of them. I know it's one ring, but it's split. Is that okay? So we call it the split ring. So this is for a DC motor. DC motor. And I'm going to tell you the use of the split ring in a jiffy. Now the split ring is this. So that there will be no tangling of this wire. This is why we use the what? A split ring. Another name for the split ring is the commutator. Now it's called the commutator because it's the one making contact for the distance, but it's reversing the direction of current. That's what it's doing. It's reversing the direction of current so that this guy will not flow in alternate directions. I'm going to explain why now soon. Now you see, then this guy is called our armature. Is our armature that is rotating, our armature is rotating in the magnetic field. These magnets are called stators. Is that okay? Because they are not moving. The magnets are stators. The stator is the part of this DC motor that is not moving. That is not moving. The armature is the one rotating. Is that okay? About a fixed point or an axis in between. So it's rotating. I mean, that's not compulsory, but now. So we have the split ring or commutator. These are battery. These are our carbon brushes. Now the carbon brushes are to make contact. Don't forget that. The split ring is to reverse the direction of current. Let's make sense of that. Let me show you a demonstration. All right, now look at this now. Let's assume this, my paper here, is my coil of wire. Is my loop, rather, my loop. So this is my loop of wire. Let me write it there. So I said that this is my loop of conductor. So that thing you are seeing here now is this loop of conductor. Is that okay? This is my conductor loop now. Now, with this guy here, I said that as the current is going in this direction here, the force will be felt downwards, right? I want you to understand the use of this split ring or commutator. As the force is pushing on, as the current is flowing in this direction rather, this guy is going to feel a force downwards, and at the same time, this point here will feel a point upward here, right? Now, if you look at it here, the direction of current wants to reverse. Do you see this? The direction of current wants to what? Reverse on this wire. So what will happen is this, that this commutator will change back this commutator. At that point here, in the beginning here, before rotation, this part was attached to this part. Does that make sense? This part was attached to this part. Does that make sense? So by the time we turn, because of that force we felt, the force of rotation, this guy here is going to feel the current is supposed to reverse, but because this commutator has changed direction to where current is coming from. Is that okay? Current will now go back again in the same direction. So that rotation, so that here again now becomes the new direction of current up. Here now becomes the new direction of current down. Is that okay? Now, if you don't still understand that in my demonstration, then you have to wait for my demonstration in the COP series. All right. So that is the way a DC motor works. Now, there was something I forgot to mention. So you understand how a DC motor works now. There's also AC motor. Is that okay? Now, AC motor, to make an AC motor, what we do is we change the split ring to slip ring. We change this split ring. We change it to a slip ring. Two slip rings, rather. Not two slip rings. One will be connected here, the other will be connected here. And that is because the AC conductor here, the AC voltage here, is going to be alternating and be trying to change the direction of this thing. The direction of the current, so that as it changes the direction of the current, it will also be reversing here. That's why we use two slip rings. Is that okay? Just think of it as the opposite of that one. Here, there's a current flowing in one direction. That's why it's direct current. Current is flowing in one direction. So, but with the movement of this thing, current wants to reverse. Is that okay? With the movement of this thing, once this thing come here, current is looking like it's going to go in the other direction. So this thing will alternate it so that current will keep entering in the same direction. Alright, but this one, alternating current already. Current is alternating. So because of that, as current is alternating, it means this thing should be, rather than just going like this, be rotating like this. It's going to be going like this and like this and like this and like this. Is that okay? So what will happen is that slip rings will be alternating the current with it so that this thing will continue in one steady direction of rotation. Is that okay? Albeit, know that this one loop is not efficient. That is why in your rotor, you have opened the rotor before, you see several coils of wire with an iron core. So that's another way to increase the rotation of this thing. I make several coils of wire. Let's say I make another coil of wire to look like to be like this. So this will not be, they'll be, in four places. I could make another coil of wire to look like this. I make another one like this. So my coil of wire is now going to be plenty. Because of that, the momentum they gain is going to be higher. Is that okay? And then rotation can be faster. So now what I said I forgot to talk about was that now if a force can be exerted on a current carrying conductor, it means that, and current is the flow of charges, right? It means that a charge also moving in a magnetic field can experience what? A force on it. Now the magnitude of the force that it feels is directly proportional, is equal to the product of the magnitude of the charge times the velocity of the charge times the magnetic field on the charge. And this in fact is called the Lorentz force. I didn't mention that before. The Lorentz force. Is that okay? Lorentz force is actually given by the product of two vectors. So we give it as Q into bracket vector Q vector V cross B. So in case we are giving vector V in the vector notation, such as we have in, like, let's say vector V was equal to 4i plus 3j or something. So you know that what you'll be taking, and B vector was given as maybe 2i minus 4j. So what you do is you take a cross product. Is that okay? Alright. If you don't know how to take cross product of this, just look at my video on, I'm going to link the video on vectors. And it's very simple. Just take them in matrix method and find the determinant. Is that okay? So that's how to work this out. No. Follow me. You see F here is given as what is Lorentz force, right? Lorentz force. F is Q times V times B. Is that okay? Now, if we know that F is equal to QVB, we can also determine direction here too. There's also direction, yes. For example, if this thing, we also use the Fleming left-hand rule. The only difference is now that this your thumb will still be the force or direction of motion. this is your forefinger, will still be the direction of magnetic field. But this time, your second hand, your middle finger here, is not going to be current again. It's going to be the what? The charge, the direction of charge. And then you have the other fingers bent like this. Okay? So this guy is going to be your Q, this guy is still going to be your B field. Now, using this again, how do we determine the direction of a charge moving in a uniform magnetic field? So let's go. Now, if my magnetic field in this my surface here is uniform and is everywhere, let's do everywhere out. Let's do everywhere into the board first. Everywhere into the board. So that is magnetic field everywhere here is what? Into the board, into the board, into the board. Everywhere on this, inside is my square. So it's uniform. It's not stronger in one place than the other. So magnetic field is into the board here. Everywhere here. Now, to stretch out, to know the direction of the charge, let's start from here. The magnetic field is going to be into the board, charge, and the magnetic field is going to be into the board. Oh, sorry. This hand is our velocity. I'm sorry. There are 3 vectors we are considering. Vector F, vector F, vector F. I'm sorry. That's not charge. Is that okay? The direction of the velocity, I'm very sorry. The velocity. So your current hand, that the middle finger that has to be current and now be velocity hand. Is that okay? So in this place, the magnetic field is into the board. Where will your velocity be? Where will your velocity be? The velocity will be rightward, right? Is that okay? If the velocity is rightward, your velocity can be anywhere, is that okay? But let's say the velocity was actually in this direction. If the velocity was in this direction, then it means that where will it feel force towards? It will feel force upward. Is that okay? If it feels force upward, the charge will now be here. Magnetic field is still here. Velocity is still in this direction. If velocity is in this direction, where will it still feel force towards? Upward, right? Now, by the time it's facing this side, the velocity, magnetic field will now still be into the board. Velocity will now be in this direction. Are you with me? If velocity is not in this direction, where will the force be felt towards again? In this direction. So the guy will move in this direction. By the time he moves in this direction, velocity has moved in that direction, right? So velocity is now in that direction. Magnetic field is always into the board as far as this case is concerned. Where will the force be felt? Down. So what do you see? The force, the charge will move in a circular path. The charge will move in what? A circular path. So for a charge that is moving in a circular path, what do we have? Remember that force we experience what? A centripetal force. So if it experiences a centripetal force, let me bring it up there. Remember that centripetal force is equal to mv squared over r, right? So let's relate the Lorentz force and the centripetal force. So we'll say that mv squared, so let's call it our first equation was F equal to BIL sine theta. However you put it, this will be equation 1. Let this become equation 2. And of course, I'm going to show you how this is generated. Or let me just quickly show you so that the video will be complete. Is that okay? Now it is generated like this. You know that the current is rate of flow of charge, right? Quantity of charge flowing per time, right? Times length is distance, and distance is given by what? Velocity times time. Velocity is equal to displacement or distance over time, right? This case is speed, right? Length, distance over time. So length will be equal to velocity times time. So in that case, this takes care of this, and what you have will be NQ, number of charges, times V. Is that okay? So that's how that formula is generated. So let's call this equation 2. Now, you already understand this scenario, right? So, if that's the case, then our mv squared over r will be equal to F equal to mv squared over r. It will be equal to this Lorentz force, which is what? F QVB sine theta also. Sine theta is the angle between the velocity vector and the B field vector. The angle between them. Is that okay? That is going to be the sine theta. So, and of course, the closer to perpendicular here too, the stronger the force. This is at theta equal to 90 degrees. That's why you have this. Is that okay? Same thing. as we had in that case. All right, so when you have something like this, then what do? So let's derive some expressions here. This takes care of this, and you see you are in formulaic approach channel, so we're going to be using a lot of formulas. Is that okay? So don't be dismayed yet. If you don't get it, just rewind the video a bit. Rewind the video. I'm trying to be to explicate as much as possible and break it down. Is that okay? And of course, you can always DM me on WhatsApp if you don't understand what I have explained. There's always a simpler way. You understand? That's why I'm here for you. By the grace of God, I want to break science down for you. Is that okay? So always, you can reach out to me on a WhatsApp line. So as I was saying, velocity cancel one of the velocities because there are two velocities here, v times v. One of the velocities, then we have mv over r is equal to what? qb. So if this is equation, let this be our equation 3, then it means that r here, already, we can begin to just, get things here. Our velocity therefore will be equal to what? From here, now be qbr over m. Does that make sense? This will be equation 4. We can also generate this thing because this thing is going to be in circular path. So we'll need the following. We'll need the angular velocity, we'll need the frequency and the period. So let's generate terms for that. You remember that angular velocity is equal to v over r. Recall this, right? Remember this. So if this is the case, that means that this part of the distance is v over r omega. So m omega is equal to qb. Does this make sense? So that omega is going to be qb over m. Does this make sense? Okay. Also remember that period rather is going to be 1 over f. If period is 1 over f, remember that if period is 1 over f, remember that omega also is 2 pi f, right? If this is the case, then f will be equal to what? Omega over 2 pi. Does this make sense? So if this is the case, then it means that inverse of this will be 2 pi over omega. So period is going to be what? 2 pi over omega, right? Okay. So it means that omega here will be equal to what? 2 pi over period. Does that make sense? So this is our equation 5. So from equation 5, you are going to need all these formulas. Is that okay? To do a lot of calculations, a number of calculations. So I'm not going to be doing that much calculation in this video. I'm going to do it in the next video, so watch out for it. But at least this video is going to help you in understanding that thing. So you have omega will now be equal to, recall that this is qb over m, right? And omega is 2 pi over t equal to qb over m. So what will be the period? We've got omega, we want to get the period now. Period is going to be equal to 2 pi m over qb. That's going to be the period. Then frequency of the movement of the charge is going to be what? qb inverse of this. Because frequency is inverse, frequency will be inverse of period, period is inverse of frequency. So qb over 2 pi m. And these are all the formulas that you need. Equation 6 and equation 7. Alright, so these are just all the formulas that you need to be able to understand that guy. Now let me solve just one question on this series, just one. So it won't look like we didn't solve any question at all. And I'm going to look for a very queer question. It's not queer, is that okay? It's not going to be strange. All right, so let me pause the video and write the question. Let me look for one. All right, now let's attempt this question. Now you see your JAMB questions will not be as long as this, or your WAEC question, I don't know, maybe your WAEC question can be as long as this, but this is a typical question under motor effect of electricity. So do well to watch it till the end, and it's very simple. An electron with kinetic energy of 1.92, so let's write our parameters. We have kinetic energy is equal to 1.92 times 10 to the power minus 16 joules. It cycles in a plane perpendicular to a uniform magnetic field. So it's going round and round in circles, right? in a plane perpendicular to a uniform magnetic field. So the plane, just like we had it there, the plane is perpendicular to magnetic field that was entering into the board in our case. The orbit radius, that is the path. Orbit is the path taken by a particle. So the orbit is 25, the orbit radius rather, is 25 centimeter, right? So radius is equal to 25 centimeter. Let's convert that to meters. That becomes 0.25 meters. You divide by 100, excuse me, you divide by 100, remove the 0, 1, 2, the point rather. Now, A, the speed of, we should find the speed of the electron. So this one is quite simple because, in fact, we need, okay, to determine speed from kinetic energy, recall, let me write this, solution. So recall that kinetic energy is given by half mv squared, right? So we need mass. I have not been given. Okay, we have the mass of electron here. Okay, good. So we have the mass of an electron. Okay, yes, it's an electron that is going in that magnetic field. Okay, the charge. Okay, so very simple. What you do is this. You just say that kinetic energy, which is 1.92 times 10 to the power minus 16, is equal to m, which is 9.11 times 10 to the power minus 31 times v squared, which is what we're looking for, over 2. You cross multiply, and then your v squared will now be equal to 1.92 times 10 to the power minus 16 times 2, all divided by 9.11 times 10 to the power minus 31. Is that okay? And you take the square root of both sides, so your v is going to be the square root of this guy. So to show me that you have been following, do this, or you follow to the end, do this and post your answer in the comment section. I'm going to see if you are correct. I'm going to tell you if you are correct or not. Alright, so that will be the answer to the first one, the square root of everything we have here. Now, what will be the magnitude, what will be the magnetic field of the, now, pardon me, I'm not solving this because I don't have a calculator with me here. There's no calculator. Did you bring a calculator? No. It's supposed to be a common calculator. Anyways, so the magnetic field, okay? So magnetic field, very simple. Since it's moving in a circular path, we said that F will be equal to, that is centripetal force now, will be equal to what? The magnetic force. Is that okay? So that will be mv squared over r is equal to QVB. This takes care of this, and we have mv over r. You see, I did not cram this. Is that okay? That's why I'm trying to regenerate it. Over QB is equal to QB. So B will be equal to what? QR over mv. So the value you get here for the velocity, you substitute it here. Mass will still be mass, and Q will now be the charge of that guy. The charge of electron is this guy, 1.6 times 10 to the power minus 19. All right. Then this even came to my mind. Mass of electron, who determined it? So it's determined by R.A. Millikan. So remember that, R.A. Millikan, in about 1915, I think. I can't remember, but it's 19th century. Using oil drop experiment. It's been asked in JAMB before. Oil drop experiment. Okay, basically, that's the way you're going to solve it. That's the formula you use for B. Solve this two, drop your answer in the comment section. So that would be B. C, the period of oscillation. So we've gotten period there. Okay, we said period here will be what? Since omega is this over T, so it means that we have 2 pi over T is equal to QB over M. So period will be equal to what? 2 pi M over QB. So use this formula to get the period. That will be 2 pi. Pi is 3.142. N is the mass, Q is the charge, and B is the magnetic field you got here. Is that okay? Do that too. That will be C. Then for the last part, okay, there's still one. D There's still one after D. D is the frequency of cycling. Okay, frequency is just 1 over T. That is inverse of what you get here. Just do the inverse. All right. Then E will now be what? What magnitude of a uniform electric field must be added to this magnetic field to make the electron move in a straight line? Okay. Okay, if the electron moves in a straight line, now listen, that's the major word there. If the electron moves in a straight line, it means that the magnetic field and the electric field are uniform, they are equal rather. So my electric field is equal to magnetic field. And remember this formula, that recall that F sub E, that's magnetic electric field, is equal to what? EQ. Do you remember? The product of the electric field intensity times the charge. So is equal to EQ will be equal to B field, which is BVQ. So Q takes care of Q. What are we looking for? What magnitude of uniform electric field? E will be equal to what? Magnetic field which you get here times velocity. And that will be your answer. Alright. So this brings us to the end of this video. I hope you've gained a lot of value from this video. Do not subscribe to the channel and click the bell notification to be notified whenever I drop a new video. God bless you. I'm still going to now make other videos after this. This video is for you to understand the concept of motor effect in one shot. Is that okay? I'm going to make other videos after this on calculation and possible JAMB question. Please, you can't afford to miss it. By the grace of God, if I have the time, I'm going to link it in the description below. God bless you. As you share the video and like it. Like it so that it can get to other people. Is that okay?